Let us go over gases, and in this tutorial we're going to understand pressure and also the gas laws. Now, say we have got a gas here. This is a manometer that we have, and this place we've left it open. And so this gas is going to be exerting a pressure in this direction. So if we have got a liquid in this manometer, because we've got a pressure that is coming from the gas, that liquid is going to be pushed. So at the beginning, if this point is closed, even this point is closed, and then you have got a gas, you have got a liquid inside. So the liquid is going to be of the same level, this side and also this side. They are going to be at the same level. Now when you have got the gas inside the manometer, and this point is also open, from this point you have got the atmosphere is going to be exerting a pressure, because we know that in the atmosphere we have got gases. So there will be atmospheric pressure from here, which I can call pressure ATM. So that is atmospheric pressure, which is being exerted by the atmosphere on the liquid in the manometer. And at the same time, the gas is also exerting a pressure. Now remember, the liquid was supposed to be at the same level. So now it will be a competition to see which one has got a bigger pressure. So the one which has got a bigger pressure is going to push the liquid all the more. So if we get to see that the liquid here is at this level and then it reaches this level, this is going to tell us that the liquid, the pressure of the gas is much higher than the pressure of the atmosphere. That is why the gas has exerted a much greater force that has pushed the liquid this far. And so to find the pressure of the gas in such a scenario, the pressure of the gas is going to be given by the atmospheric pressure plus the height. Now the height is simply this difference here between this point where the gas is and that point where this point where the liquid is at this point and that other point. So that is going to be the height. So this is how we're going to be able to determine the gas pressure. What of if we have got this side, the the liquid reaches at this point? Of course we still have the gas here, but here the liquid is at this point. What does this tell us? So from this scenario we can see that the pressure of the atmosphere is much higher than the pressure of the gas. Therefore, to find the pressure of the gas, it is going to be given by the pressure of the atmosphere and then minus h. So instead we are going to remove this height, because this height is not just showing anything, it is showing the pressure. So this height is also representing pressure. So this is how we're able to determine the gas pressure. So I mean that if I want to determine the atmospheric pressure, actually when you are finding the atmospheric pressure in this setup, it's going to be given by, if you are determining just the pressure in this setup, the total pressure is going to be atmospheric pressure plus pgh, where this is density of the liquid, gravity, and then height of the column that has risen. So what I want us to understand is just these two equations which I've written here. So the pressure of the gas, depending with how the column is going to be given by those two formulas. Now how do you get to measure pressure? So the pressure of the gas is given by the height, which is the height difference as we saw in the previous diagram. That is going to give us the pressure of the gas, and that is the difference in mercury levels. And so the liquid that we get to use in the manometer is the mercury. So now what will be the unit of pressure? We know that height is measured in meters, is measured in centimeters, can be measured in millimeters. So in this case, since we are using mercury, actually the pressure is going to be measured in millimeters of mercury. Now a millimeter of mercury is a unit that is equal to a torr. A torr is another unit for pressure. So what we're able to see is that 1 millimeter of mercury is equal to 1 torr. Now we also have a related unit for pressure, which is called the standard atmosphere, ATM. That's another unit for pressure. So when you're talking about 1 atmosphere atm, this is going to be equal to 760 millimeters of mercury. Now we know that millimeters of mercury is equal to a torr, so this is also going to be equal to 760 torr. So this is the atmospheric pressure. 1 atmosphere is referred to as the atmospheric pressure. It is a standard value. Now at the same time, 1 atmosphere is also, so pressure is not just measured in atmospheres, millimeters of mercury, torr, it has got a lot of units. So this atmospheric pressure, or the pressure of the atmosphere, is also equal to, we can as well measure, because we know that pressure is given by force over area. And you know that force is measured in newtons, area is given in meters squared. So this is another unit for pressure, which is a newton per meter squared. Now the unit newton per meter squared is equal to a pascal. So meaning that 1 newton per meter squared is equal to 1 pascal. So when you're comparing an atmosphere with a pascal or a newton per meter squared, 1 atmosphere, which is atmospheric pressure, is going to be 101325 pascal. In other books, you just see this one written as 1.01 multiplied by 10 to the power 5 pascal. So these are some of the units that we get to use when you are measuring pressure. So from all of these, the SI unit for pressure is the newton per meter squared, which is the same as a pascal. So meaning that mostly if you have been given questions to do with pressure and they've given you maybe in atmosphere, millimeters of mercury, or in a torr, you need to get to convert to a pascal, a newton per meter squared, because that is the SI unit for pressure. But if the units are uniform, we all have millimeters of mercury, we can just get to use that in the equation. So that is a basic introduction to this, right? So I can give an example. When you have been given 49 torr, you want to convert this to a pascal. How do you go about it? So we have got 49 torr. To convert this to pascal, I'm going to multiply. Because I've got a torr on top here, I'm going to bring a torr down, and then I'm going to put a pascal on top, right? Firstly, before I go to a pascal, I have to convert, because I've got a relationship between a torr and an atmosphere. So I'm going to first go to ATM. Now we know that 1 atmosphere is equal to 760 torr. Okay, so and then from here we are also going to convert. So this torr and the torr is going to cancel out. I want to go to pascal, so I'm going to remove the ATM. So I'll put ATM down, and then I'm going to put pascal on top. Again, we know that 1 atmosphere is 101325 pascal. So the atmosphere and the atmosphere is also going to cancel. So therefore the answer is going to be 6.5 times 10 to the power 3 pascal. So this is the conversion that gets to happen. So let's also get to understand gas laws. So since we are discussing gases, we need to know the laws that gets to apply to gases. And mostly when you're talking about these laws, they apply not to real gases but to ideal gases. We are going to understand that what that is. And the first law that we can talk about is the Bohr's law. What does Bohr's law tell us? So Bohr's law is going to give us the relationship between pressure and volume. So we are going to see that volume is actually inverse proportion to pressure. So if we want to put this in words, we will say the volume of a gas is inversely proportional to the pressure at constant temperature. So when you're talking about the Bohr's law, we don't have temperature in this equation. So from here I can get to rewrite this, and that is going to give us volume being equal to, because I've introduced the equal sign from a proportionality symbol, I'm going to have a constant of proportionality, and then we're going to have pressure. So this is going to give us K being equal to volume multiplied by pressure, or pressure multiplied by volume. So this K is a constant, meaning that if I have got K and then we have got P1 and V1, and then I have got K for the same gas, I've got P2, V2, we are seeing that K is the same. So I can just get to equate these two equations, and then we're going to have P1, V1 being equal to P2, V2. So this is all coming from Bohr's law. Tells us that the volume, or I can as well say pressure, is inversely proportional to the volume. So the pressure of a gas is inversely proportional to the volume at constant temperature. So this one is Bohr's law. So if we want to get to sketch the pressure against volume, we can see that from this equation we have got pressure, and then we have got 1 over volume. So if we are able to sketch the equation of pressure against 1 over volume, is going to go as a straight line like this. We have got pressure here, we have got 1 over volume. But if we are not using 1 over volume, say we are using volume, we have got pressure here, we've got volume. We know that when we are increasing pressure, since the inverse proportion, when we are increasing pressure, volume is going to be reducing. When we are increasing volume, pressure is going to be reducing. So this is going to be the graph. Now when we plot a graph of pressure times volume, let's say I've got pressure multiplied by volume this side, and then this side we can have, let's say, pressure. So different equations, we can have different lines. We can have a line that goes like that, we can have a line that goes like this, a line like that goes like this. Now the line which goes straight like this, giving us pressure and volume being constant, this gives us what we call an ideal gas. Now real gases might differ from the ideal gas. Pressure times volume might not necessarily give us a constant, as we have seen here for real gases. So what is an ideal gas? An ideal gas is a gas that strictly obeys Bohr's law. That is what we call an ideal gas. So this is the equation that comes from Bohr's law, telling us that if you get to multiply pressure and volume, that is going to be a constant. So I can just get to write this. PV is going to be equal to K. The next gas law that we can be able to understand is Charles' law. So how about Charles' law? So Charles' law is going to relate volume and temperature. Remember, this one was just relating volume and pressure. So this one relates volume and temperature. And from Charles' law, we have the volume of a gas being directly proportional to the directly related or directly proportional to its temperature in Kelvin at constant pressure. So what we are saying is volume is proportional to temperature. This is absolute temperature, or temperature in Kelvin. And here pressure is held constant. So from here we can derive an equation to say volume is actually equal to K multiplied by T. If I want to remain with K, therefore K is going to be V divided by T. We can deduce an equation to say V1 over T1 is going to be equal to V2 over T2 from the Charles law. Or I can cross multiply. We're going to have T1 V2 being equal to T2 V1. This is the equation that comes from Charles law. I can as well write that to say V over T is equal to K. The next gas law that we also get to understand is the Avogadro's law. Now what does this one get to relate? So Avogadro's law is going to tell us the relationship between volume and the number of moles. This one is going to tell us that equal volumes of gases at the same temperature and pressure contain the same number of moles. So meaning that if I've got the same volume of gases, these are going to have the same moles. If this one has got 2 moles, this one is also going to have 2 moles because they are equal volumes. And so from here we can deduce the equation to say volume is equal to K multiplied by N, because we are saying volume is proportional to the number of moles. So if I change this into an equation, that will be volume is equal to Kn. We can make K sub the formula that is going to give us volume divided by N. So these are the three gas laws that we have to understand. Now, let's say we've been given a gas. Let's say we've been given sulfur dioxide, and it is found that when we have got 1.53 liters of sulfur dioxide at a pressure of 5.6 times 10 to the power 3 pascals, when you get to change the pressure, and let's say we get to change the pressure changes to, so what we've been given is the first one, so this one here is going to be V1, this is going to be P1. Let me just get to write that. So let's say we've been given V1 as 1.53 liters, and then we've been given P1 to be 5.6 multiplied by 10 to the power 3 pascal. So we now change the pressure, and at the end what we have is P2 is 1.5 times 10 to the power 3, let's say to the power 4 pascal. So we are talking about at constant temperature. Temperature isn't changing. Okay, so the question is, what will be the new volume now? What will be V2? So from here we can determine what gas law are we going to use if we are talking about the relationship between volume and pressure where temperature is constant. So this is going to be Bohr's law. We know that from Bohr's law, pressure and volume are inversely proportional. And from there we get to say P1 V1 is going to be equal to P2 V2. So we already have P1, which is 5.6 times 10 to the power 3 pascal. We need to take note that the unit should be the same on both sides of the equation. V1 is 1.53 liters and P2 is 1.5 times 10 to the power 4 pascal. We don't know V2, so I have to divide both sides by 1.5 multiplied by 10 to the power 4 pascal. So therefore V2 is going to remain, as we can see that the pascal is going to cancel the pascal, so we expect the answer to remain in liters. That's why we make sure that the units are uniform, and this is going to give us 0.57 liters. So that is it. That is how we are able to work out such a one. Let's have another simple one. Let's say we've been given a gas, just any gas, and we've been given temperature 1 of this gas to be 15 degrees Celsius, and pressure 1 we've been given as 1 atmosphere, and it has got a volume, that is V1, of 2.58 liters. Okay, so this is what we have now. What volume will the gas occupy? What volume will the gas occupy if the temperature, that will be T2, now is 38 degrees Celsius, and then the pressure is still 1 atmosphere? So I want to find out the volume that this is going to occupy. So from what we are able to see, pressure is constant. So we are talking about a gas law that is going to relate volume with temperature where the pressure is constant. Which one is that? That is Charles' law. So from Charles' law we know that V1 divided by T1 is equal to V2 divided by T2. So from here we can get to substitute. Now what we need to take note is that the temperature that we use here is absolute temperature, the temperature that is in Kelvin. So this one has been given in degrees. So let me first convert T1 from degrees to Kelvin. So when you're converting temperature to Kelvin is given by temperature in degrees plus 273. So therefore T1 is going to be 15 plus 273. In some books you see 273.15. So this is going to give us 288 Kelvin. And then T2 is going to be 38 plus 273. And that is going to give us 311 Kelvin. So I get to substitute V1, the first volume, that is 2.58 liters, T1, that is 288 Kelvin. That is going to be equal to V2, which is the one we are looking for, divided by T2, which is the 311 Kelvin. So I'm going to multiply these two values. That is going to give us 2.58 liters multiplied by 311 Kelvin. I was supposed to multiply the 288 Kelvin with a V2, but I want our V2, so instead I'm going to divide both sides by 288 Kelvin, and this is going to be able to give us V2. So see, the Kelvin and the Kelvin is going to cancel out, so therefore our answer will just remain in liters, and that is going to give us 2.79 liters. Let's consider also another example here. So let's suppose we have 12.2 liters sample of oxygen, right? We have got, that is volume 1 of oxygen, that is given as 12.2 liters, and it contains the first number of moles, 0.5 moles, at a pressure, which is P1, of 1 atmosphere, and at a temperature, T1, of 25 degrees Celsius. Okay, now if all of this oxygen which we have was converted to ozone, which is O3, at the same temperature and pressure, meaning that pressure 2 is still going to be 1 atmosphere, and then temperature 2 is also going to still be 25 degrees Celsius. But remember, we have converted the oxygen to ozone, so that will be V2. What will be V2 of O3? Okay, what will be the volume of the ozone? That's the question that we have. So what are we able to determine from here? And of course, the number of moles, the second number of moles, should be able also to put the value here. Now when you get to convert oxygen to ozone, what gets to happen? We have got oxygen converted to ozone. Whenever you're talking about chemistry, we always make sure that we use balanced equations. And so to balance this equation, I'm going to put a 3 here, I'm going to put a 2 here. So we're saying that when we have got 3 moles of oxygen, that is going to convert to 2 moles of ozone. So therefore, we're going to give the relationship number of moles of oxygen divided by 3 is going to be equal to number of moles of ozone divided by 2. So the number of moles of oxygen, we already have the number of moles of oxygen already given. That is 0.5. That divided by 3 is going to give us the number of moles of ozone divided by 2. So to remain with the number of moles of ozone, we'll get to multiply these two terms, to multiply by 0.5. And then this value which is supposed to multiply the number of moles of ozone, we are going to divide. And so this is going to give us 0.33 moles of ozone. Now that we know the number of moles of ozone, what equation can we use to find the volume given the number of moles? We are going to use the Avogadro's law. And from the Avogadro's law, we know that V1 over N1 is equal to V2 divided by N2. So V1 in this case, we've already determined, or it's already given, that is 12.2 liters. N1 is 0.5 moles. This is going to be equal to V2, that is what we want, divided by N2, which is the 0.33 liters we've determined. Therefore, V2 is going to be the product of 12.2 liters and 0.33. Sorry, this is supposed to be moles, and then divide that by 0.5 moles. The more gets to cancel, so the volume of the ozone that is going to be produced is going to be 8.1 liters. So this is how you get to work out this one. All right, now we can be able to combine the three equations or the three laws that we've talked about: the Bohr's law, the Charles law, and also the Avogadro's law. So from the Bohr's law, what did we say? So the Bohr's law gave us to say volume is actually constant. I can first write that the way we wrote it. We know that K is equal to PV. That's from the Bohr's law. Then if we go to the Charles law, we found that K is going to be V divided by T. If we go to the Avogadro's law, we found out from this one that K was equal to V over N. Now in these equations, we can see we have volume. Volume is something that is present in everything. So on the Bohr's law, temperature and number of moles is constant. On the Kelvin law, pressure and number of moles is constant. On the Avogadro's law, the temperature and pressure constant. Let me make volumes out of the formula. So in the first one, we're going to say that volume is going to be equal to K divided by P. In the second one, we are going to find that volume is going to be K multiplied by T. In the third one, we're going to find that volume is going to be equal to K multiplied by N. Actually, this is also multiplied. So from this, we can see that volume is proportional. On top, we have got K, all right? So I'm not going to talk about K because K is constant. So you can see that volume is proportional to temperature. It is also proportional to the number of moles, but inverse proportional to the pressure because it's in the denominator. So from here we can derive a new equation to say volume is going to be equal to, now because I've changed the proportionality symbol into an equation, we are going to have a constant. Now in this case, we are going to use what we call the universal gas constant R, and then we are going to have T and then N divided by P. So from here we are going to cross multiply the pressure and the volume. So we're going to have PV giving us, I'm starting with N and then R and then T. So this equation which we have here is called the combined gas law or the gas law equation. This is going to relate all the components that we've talked about. At some times we can also get to simplify this one further. We are saying that PV is equal to N RT. If I get to divide both sides by volume, this cancels with this one. We're going to see that pressure is equal to, if we say number of moles divided by volume, this gives us molarity. So we're going to have molarity multiplied by universal gas constant multiplied by temperature. The temperature is in Kelvin. So we can as well get this equation from the gas law that we have. Right. So let's consider this question. A sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5. Calculate the moles of hydrogen gas molecule present in the sample. So what have we been given? We've been given V1 as 8.56 liters. Been given temperature 1 as 0 degrees Celsius, which when we want to convert to Kelvin, we're going to add 273. That is going to give us 273 Kelvin. And we've been given pressure, which is 1.5 atmosphere. Now I want to calculate the moles of hydrogen. How do you get to calculate the moles of hydrogen? We know that pressure, so we don't have number of moles here. Pressure multiplied by volume is equal to N RT. And so this is going to give us pressure, which is, now again here we have the universal gas constant. So the universal gas constant has got different values. So the value that you are going to use is depending on the units of volume, temperature, pressure that you've been given. Okay, so let me just get the universal gas constant, the different values it gives us. Right, so the universal gas constant is going to have all these values. We are going to have 8.314 joule. Like, we can even determine the unit of the universal gas constant from here. I can make R sub to the formula. Maybe we just get to see that. So I'm going to divide both sides by N and T. So therefore R is going to be PV divided by NT. So R can be, if we are using pressure in atmosphere, then R is going to be atmosphere volume, let's say, is given in liters. So that will be atmosphere liter per mole, let's say temperature is in Kelvin per mole Kelvin. So this is going to be a unit for the universal gas constant. If we are using pressure in torr, then that is going to be torr, let's say volume is in milliliter, so torr milliliter, and then number of moles is still in mole, we can have more Kelvin. So just depending, now the mole and the Kelvin are in the denominator, so put per, or I can put to the power negative 1 to the power negative 1 because they are in the denominator. So depending with what units of pressure volume we are using, we get to use different values of the universal gas constant. So we have got 8.314 joule per mole Kelvin. Now when we get to the joule, when you multiply pressure and volume, that is going to give you work, and work is given in joules. So when you're talking about energy, you are going to use this unit of the universal gas constant. You can as well use 0.08205 liter atmosphere per mole per Kelvin. This is another one that we're able to use. Another one we can be able to use is 62.363 millimeters of mercury liter per mole per Kelvin. So there are different ones that we are going to be able to use depending with the units that have been given. So if we get to look at this equation, what are the units of volume and what are the units of pressure? So pressure is given in atmosphere. So we're going to look for something that has got the atmosphere. So this one has got liter, this one has got atmosphere. So we can see that this is the one we are going to use because also the temperature is in Kelvin. Actually, you always need to convert temperature to Kelvin, right? So we'll just get to substitute that. So pressure that we are able to see is 1.5 atmosphere. I can also include the unit. Multiplied by volume, which is 8.56 liters. That will be equal to number of moles which we want, multiplied by R, the universal gas constant. What are we going to use? We are going to use 0.0820. In some books we are going to see 5, in some books we are going to see 6, but depending with what value you've been given in the exam paper, that's the one that you are going to use. So this one is given in liters atmosphere per mole Kelvin, then multiply by the temperature, which is 273 Kelvin. Okay, so from here, this Kelvin which is in the denominator, I'll cancel the Kelvin from this equation which we've written. This liter will cancel with this liter this side. This atmosphere will cancel with this atmosphere this side. So the only unit that is going to remain is a mole. Alright. So to remain with the number of moles, we divide both sides by this value here. So therefore number of moles is going to be 1.5 multiplied by 8.56 and then divided by 0.08206 multiplied by this one is multiplied by 273. And this will give us the number of moles to be 0.57 moles. Let's consider the next one. A sample of ammonia gas with a volume of 7.6 liters at a pressure of 1.6. So volume is 7.6 liters. Pressure is 1.68 atm. We've been told it's compressed to a volume. So this was V1. So was pressure 1. Now it has been compressed, meaning that the volume has been changed. So now you have got V2 as 2.7 milliliters. So now what will be the final pressure P2. What equation can we use relating volume and pressure? This is the Bose law. So P1 V1 is going to be equal to P2 V2. So P1 is 1.68 atm, V1 is 7.6 liters. That is going to be equal to P2, which we don't know, multiplied by V2. Now you can see that V2 has been given as 2.7 milliliters. So we have to convert the milliliters to the right unit. That is the unit of what? In the same unit as the other one, it should be in liters. So we're going to say 2.7 milliliters. We'll get to multiply. I've got a milliliter on top. I'm going to put down, and then a liter on top. We know that in 1 liter I've got 1,000 milliliters. So if we get to divide 2.7 by 1,000, we are going to get 0.0027 liters. So just get to divide both sides by 0.0027 liters, also the other side. The liter will cancel out, therefore P2 is going to remain. I'm going to multiply 1.68 by 7.6, and then I'll divide by 0.0027. That is going to give us 4. Let me just get to punch that again. 1.68 multiplied by 7.6 divided by 0.0027. So this one has given me 4,728.9. The unit is going to be in atmospheres. So this is going to be the value. We see that the pressure is much higher because the volume was too small. This one is actually in milliliters, so it was very small. Let's consider this one, a sample containing 0.35 moles of argon. So the number of moles is given 0.35 moles, and then we've been given the temperature at 13 degrees Celsius. Can actually just add 273 to convert to the right unit. So 13 plus 273, that is going to be 285 Kelvin. And the pressure, also been given pressure of 5082. Okay, so this is number of moles 1, temperature 1, pressure 1. Now we've been told it is heated to the temperatures, and everything is going to change. So temperature 1, temperature 2 in other words, is now 56. So we are going to add to 273. Okay, so this is going to be 56 plus 273, and that is going to give us 329 Kelvin. And then the second pressure, that is P2, is 897 torr. Now the question is calculate, actually it's supposed to be calculate the change in volume that occurs. So the change in volume that is going to occur. Now how are we able to calculate the change in volume? From the relationship that we have, we can see number of moles, temperature, and pressure. Now we want to find volume. On the first one, we don't see any volume there. So the first thing that I'm going to be able to find is I'm going to find the first volume, right? If I find the volume here and then I'm going to find the volume here, I can now find the change in volume. So we know that P1 PV is equal to nRT. So the first pressure, or I can make volumes of the formula, at the first pressure given, that is 508 torr, multiplied by volume, that will be equal to number of moles, which is 0.35, multiplied by the universal gas constant. We are going to use 0.08206, depending on the units that we have, right? And then also multiplied by the temperature. The temperature is 280. That is 285, because we did 13 plus 273, 285 Kelvin. So we'll get to divide both sides by 508. Therefore the volume is going to give us 0.35 multiplied by 0.08206. 0.08206 also multiplied by 285, then divide that by 508. That is going to give us, so from what we are even using here, I hope we took note of that one. The pressure that we had, remember when I gave the R was 0.08206. This one was given in liter atmosphere per mole Kelvin. Now the temp pressure that we have is not in atmosphere, it is in torr. So that was, I should have first converted the pressure to atmosphere, otherwise the universal gas constant that I'm using in this case has got atmosphere. Now the pressure is in torr, so that is going to give us a wrong answer. So let me convert the pressure, that is 508 torr. We are going to multiply, we are going to put a torr down and then atmosphere on top. We know that in 1 atmosphere we have got 760 torr. So this is going to give us 1.18 atms. Sorry, not this one I've used for the other one. 508. So this value is 568. I wrote 508, so that is 568. So 568 divided by 760, that is going to give us 0.747 atm. So that's the one we are going to use. 0.747 multiplied by volume, that is going to be equal to N, which is the number of moles, and that is 0.35, and then multiplied by 0.08206 multiplied by the temperature in Kelvin, which is 285. So the volume that we're going to find is about 11 liters. That's the first one. Now again, we need to find the volume here. Now we can't find direct the volume because we don't know the number of moles. So what is going to happen? So from what you've been told, we get to heat this substance to this pressure. So we expect that the number of moles are going to remain the same, because when you're talking about number of moles do not change. The moles of a substance are always the same. So say also PV is going to be equal to nRT. So the pressure in this case, same, we've been given in torr, so we need to convert this to atm. So we're going to divide by 760, and that is going to give us 897 over 760 is 1.18 atm. So that would be 1.18 multiplied by volume is going to be, because number of moles is the same, they don't change. Universal gas constant 0.08206, then multiply that by the temperature. The second temperature which we have is 329. Therefore, if we get to divide both sides by 1.18, this is going to give us a volume of 8 liters. The question is find the change in volume. So change in volume is given by final volume minus initial volume, 8 minus 11. That is going to give us a negative 3 liters. So meaning that the volume changed for this, the volume decreased. That is why the change is negative.